So flocculation. So we're going to talk about how do we separate contaminants from water, because there's some things in the water that we don't like. Yeah, we figured out how to measure the flow. We know how much is coming into our plant, but there's some things in that water that we'd like to get out, and that's the whole point of this course. And we'll discover that sedimentation is a really awesome separation technique, but it's too slow for a lot of the things that we want to remove. And so we're going to figure out how to gang up on gravity using flocculation. And we're going to talk about sticky nanoparticles. So these are, if you're going to separate two things, there has to be something different between those two things so that you can separate them. And the differences might be, you know, the color or the density or electrical charge or something. So here are options for differences that you could potentially exploit. And you'll see that even though there are many different things that we could potentially measure, and I guess I should have added something like there could have been smell, right? There could have been some other interesting characteristics that we could have used to separate things. The ones that we end up using in our water treatment plants are really size and density for the processes that we're covering in this class. There would be a whole other class of things that we could talk about related to using things like activated carbon or ion exchange resonance. But even if we went down the path of thinking about membrane filtration, or if we thought about reverse osmosis, we'd effectively be talking about size. We're using the fact that the water molecules are tiny compared with some of the other molecules that we're trying to remove in those cases. But we're talking at an even bigger scale, still small scale, but even bigger scale. We're going to use size and density to remove things. And let's go to the problem. We'd like to use sedimentation to separate out the particles that we don't want. We'd like them to drop to the bottom or float to the top, I suppose. And so there's our little particle, and we're going to look at the forces that are acting on it. And we know that the sum of the forces equals mass times acceleration, but this guy is not accelerating. So I suppose we're going to say that there's a couple different forces acting on it. There's its weight that's pulling it down. That's gravity acting on it. There's a buoyant force that's tending to pull it up. And there's a drag force that's tending to pull it up, assuming that this thing is moving down. And so those three forces have to sum to zero because it's not accelerating, okay? And the weight of this object is just equal to its volume times rho and g. So the density, and here I said I'm talking about a flock. So the density of the flock and times the acceleration due to gravity. The buoyant force is just the volume of the flock times the density of water times gravity. You probably remember buoyant force from fluid mechanics. So that's the net force acting up, or the force acting in the upward direction. And then there's this drag force, and this drag force equation comes from fluid mechanics. It's dimensionally correct, makes sense. It's some coefficient of drag times the projected area of the flock, and times, and it's interesting, this drag force, the density that's in that drag force equation is the density of the fluid, because the drag is caused by the fluid. So it's not about the density of the flock. Is that clear? If you're thinking about the drag force on your car when you're driving down the road, the density of your car has nothing to do with it. It's only the density of the air that matters. So in the same case here for our flock, the density that matters is the density of the fluid. And then of course, times its terminal velocity, its velocity squared over 2. So we can set all those, you can use FD plus FB minus W, the force of drag plus the force of buoyancy minus weight is equal to 0. We've got equations for those three forces, and we can solve for the terminal velocity. Okay, so I just tuck those three equations together, solve for the terminal velocity, and I have this beautiful general equation for how fast will a thing that can be characterized by a diameter fall? And so if you could characterize a human as spherical, this would work for humans falling in air, as well as for a cryptosporidium that's settling in water. It all works. And then here's the next part, and that is this drag coefficient is like the big unknown, and that's what's needed to solve this equation. The drag coefficient, unfortunately, is not a constant. It's a function of the Reynolds number, and it's a complete mess. And I would love it if you would see that this graph is so similar to one other big graph that I showed you in this course. It is the Moody diagram. So yes, it's describing exactly the same thing as flow through a pipe. It's just that this time it's flow around the sphere. So the geometry is a little bit different, but in both cases it's flow, and the fluid, the laminar and turbulent makes a big difference. And in both cases, it acts completely different in laminar than it does in turbulent. And in both cases, it flattens out at high Reynolds number, with the added complication that there's a little bump in this curve out around like 100,000. It's high, and then it drops down by the time it gets to about 300,000. And that little bump is when the boundary layer around the sphere gets turbulent. And just because I like fluids, I'll have to bring in this a little aside. This is why, if you play golf, the golf balls are dimpled, because the dimples on the golf ball help the boundary layer transition to being turbulent a little bit earlier than it normally would be. And it makes the golf ball have a turbulent boundary layer. Turbulent boundary layer means the boundary layer gets a little bit smaller, and that makes the wake behind the ball a little bit smaller, and so it has lower drag. So this is an odd effect where turbulence in the boundary layer actually makes lower drag on an object. And so now, because all of you are extremely interested in saving the planet, right? Like you're trying to reduce how many fossil fuels you use, and you're trying to, I don't know, reduce, or you're trying to improve the efficiency of your car. And so now you're thinking that you're going to go out to your car with a ball peen hammer, and you're going to put little dimples throughout the car so that it gets better fuel mileage, right? Now I realize I'm going to be in really big trouble, because some of you are going to do this later today, and then there's going to be all these unintended consequences. Okay, so anybody know why that's not going to help? This bottom Reynolds number is V times D over nu. So V is how fast the car is traveling. D is, okay, some width of the car or height of the car. And you're comparing that with a golf ball. So the Reynolds number for a car is higher, given if it's traveling at a similar speed. So the car already has a turbulent boundary layer. And so putting lots of dents in your car won't actually help, and it might cause some people to be angry with you. Okay? Now you know why you won't take the ball peen hammer to your car. Okay. Happily, like this equation, this is a mess. This is just like on the pipe side, using the Moody diagram was a complete mess. And I told you, please don't use the Moody diagram, use equations that capture that instead. We'd like to do a similar thing here. And what's going to save us here is that most of our world with removing particles in water treatment processes is small enough and slow enough that it's all in the laminar range. And so we can use that laminar range where it's just a straight line on a log-log plot. And we can use Stokes' law. And just like on pipes where there was 64 over the Reynolds number showed up as this nice relationship for F. For laminar, here coefficient of drag is 24 divided by the Reynolds number, so another beautiful, simple relationship. And that means that we have two different equations that we can use. For turbulent, we just take, hang on. For turbulent, we just take this equation that was at the bottom of the previous slide. Okay, that is the general equation. It's always true. It's like Darcy-Weisbach. It's got an F in it and it's always true. This one has a coefficient of drag in it and it's always true. For the specific case where we have laminar flow, we can replace the coefficient of drag with 24 over the Reynolds number, and we can replace the Reynolds number with the velocity times the diameter divided by the kinematic viscosity. And when you do that, you get velocity shows up on both sides of the equation, but happily, you can easily factor it out again. And so you can solve for velocity and you get the new equation that I've shown now at the upper left of the slide. And so that is a beautiful, simple equation that only works in laminar flow. It's like the Hagen-Poiseuille equation in pipes. And it's going to be very, very useful for us. We're going to be using that equation plenty of times. And here's the question. Given that that's the equation, will a bacteria cell settle fast enough that we can just use sedimentation to get it out of the water? And so this is just taking that equation and plugging in like order of magnitude estimates for the various things. So a bacteria cell is 10 to the minus 6 meters, right? It's a micrometer in diameter. So when you square that, you get 10 to the minus 12. G is about 10. The density of a bacteria cell is it's close to 1,001 kilograms per meter cubed. And the density of water is 1,000 kilograms per meter cubed. And so you end up with that whole term, rho bacteria minus rho water over rho water ends up being 10 to the minus 3. Because that small difference between water and bacteria. Viscosity is about 10 to the minus 6. And you crank all that through and you get a terminal velocity that's it's on the order of 10 to the minus 9 meters per second, which is a nanometer per second. And I don't know when the last time was that you watched, a race that was happening at a nanometer per second, but it's kind of boring. And we basically can't afford to wait. And there's another problem, and that is when you are settling this slowly, there are other things that are happening that are moving you around randomly that are going to end up mixing you back up. And that is something that we have no experience with as humans at our scale. But at the scale of a bacteria cell, you notice it when you get hit by a water molecule. And you actually move a little bit every time you get hit by another water molecule. So diffusion, molecular diffusion, the fact that water molecules are bouncing around because they've got thermal energy, that's moving the bacteria around as well. And that means that, and that rate is actually faster than this terminal velocity. And that means that diffusion is going to help keep that bacteria cell in suspension, and it's never going to settle out. So that was grim, and it would suggest that if we're trying to remove pathogens from water, sedimentation is not a good option. But we're going to apply a trick. How could we somehow mess with this equation so that we could improve our ability to remove things? So our problem was that the terminal velocity was much too small. So how could we increase the rate, the sedimentation rate for small particles? How could we get small particles to settle fast